Here we want to demonstrate our system for measuring insertion loss and polarization dependent loss, or a dependence of wavelength and polarization for optical components that we test in the networks. And this is one of the basic and fundamental measurements that are made now also for photonic integrated circuits, wafer level or chip level measurements. And so we want to go into those details because we've got new instruments and software that really support this function. So this is a setup that we start with generating an optical signal with a tunable laser. This is one that can sweep over a 200 nanometer wavelength range, including the C-band and L-band, which are most relevant for DWDM transmission systems, for instance. And then we take the signal to a polarization controller. This is a special unit able to, or model that can switch polarization very quickly and monitor and log the polarization at the same time, so that we can switch the polarization over a set of chosen polarization states while we sweep the wavelength, and therefore make a polarization dependent swept wavelength measurement with a single sweep. And that allows us to collect all of the polarization information in a short time, less than a millisecond actually, for any particular wavelength point. And that gives us very high resistance to interference from vibrations or temperature drift, for instance. And finally, the signal in this case will be picked up by one of our new optical power meters. In this case, we've got 8 optical ports, and we're going to measure our reference measurement here, and then we'll connect our device under test on these ports. We can also make the same kind of measurement on devices with integrated photodiodes by using source measure units to detect photocurrent instead of the output light of the device. Okay, so let's take a look at how that works with our software. Okay, I've just started the software. It's recognized the instruments and checked to see that they're connected correctly. And now, since this is an L-band multiplexer that we're going to take a look at, we've selected a wavelength range from 1560 to 1610 nanometers. And I'll do that to get sufficient resolution at 20 nanometers per second. A 6 picometer step is a good setting. We could use 5 or 10. And we'll make our reference measurement. And I'm going to make a new reference on port 1. So the first thing this does is identifies the states of polarization that are going to be used, so that we can afterwards switch through them very rapidly, like every 50 microseconds. Okay, that looks good. Just to check, I can take a measurement on that same port. It's always kind of a good sanity check to make sure the connections were good. And here we see the insertion loss is within a couple thousandths of a dB. So this is where we want to be for our loss measurement. Now we'll go ahead and connect the device under test. And we're going to move or copy the reference data to the ports that we're using for that measurement. So I say copy reference from here. Of course, all this can be done automated from another program so that these measurements could run in much more quickly, but we're doing it manually here with our GUI. 4 output ports of the multiplexer device, and we'll take the same fiber that we used for the reference measurement and connect that to the input of our device under test. And with that, we should be ready to make a measurement. if we switch to our IL-PDL layout, then you can see we have for those 4 ports the insertion loss and the polarization dependent loss. I've got that up to about 60 dB dynamic range. And now using a double sweep, we can extend that dynamic range to about 80 dB dynamic range. So you can see, I can zoom in. These are channels that are spaced exactly 100 gigahertz apart, according to the ITU grid. So we might want to look at that on a wavelength scale. And here you can see for each 100 gigahertz, we've got one of our channel ports. We can also analyze those with the DWDM analysis, choosing the 100 gigahertz setting. We could choose a limited wavelength range if we wanted to, or just use the wavelength range that we measured. And this gives us now things like the offset from the nominal wavelength, center wavelength, the loss at the center of the nominal channel, channel isolation to the nearest neighbors are in this case all above 42 dB, even higher in some cases, and for non-adjacent channels beyond 75 dB, actually quite a bit higher. We've also got values for the PDL in the channel, loss in the channel. So these are all the terms that are defined by the ITU for characterizing bandpass filters. So that's a fundamental measurement for a lot of optical components, especially wavelength selective components like multiplexers for WDM, also for wavelength selective switches, interleavers, a lot of these devices. And now I would like to show how we've adapted the software to also consider devices that are where we couple the light into them through an optical probe, and grating couplers, for instance, which are strongly polarization dependent. And so for that test, I'm going to connect a polarizer to the input of the device under test, and then we'll show how those measurements look and what we can do with them with our software. Okay, so now we're back at the same setup, except that we've inserted a polarizer at the input of our device under test. We're going to run that measurement again. I'm going to make one change in our settings and disable auto gain, which we use to extend the dynamic range of the power meter somewhat, but interferes with measuring a very strong polarizer. And we'll make that measurement now. Okay, and now we've got our 4 filters again on the wavelength scale, or that was the frequency scale. I can switch to the wavelength scale, and you can see that in band the polarization dependent loss is now well above 20 dB, which is pretty much the range that we can get to with the matrix analysis we're making for these polarization dependent measurements. And now what we can do, first of all, we could show the same curves showing the minimum and maximum PDL, or TE and TM. And those are also showing more than 20 dB difference between the, say, the TE and the TM direction in this case. So what I'm going to do is set the laser and the polarization state now to match this port at the state for maximum signal. For that we can use our static mode. I've chosen port 6 and that wavelength range of 1598. And here I've chosen to use that measurement to set the maximum. So I can say set static. That's been done. And now I can go through and say I want to make the same sweep, but without polarization resolution. Okay, and now you can see we've got, again, our 80 dB of dynamic range, and we've got our signal up at showing the insertion loss of the polarizer in this case when our signal is aligned with the polarizer, so the maximum transmission. And in this case, now since I don't need to take 6 states for each state of polarization, we could also sweep faster. And that can be of interest if, for instance, we want to be able to step from one device on a wafer to the next device on the wafer and repeat the measurements, and we can do that in a couple seconds in this case. A couple further notes. With this, we could now read the current settings, and I could choose to now set the orthogonal state of polarization and make a sweep. In this case, that won't be very interesting because there will be hardly any light, but we could do the same kind of measurement that way. And the other feature that we've got on this software now is very useful for especially fast automated measurements is the ILD embedding that allows us to make measurements of the difference in optical paths, for instance, for optical switches that are used to choose a device under test or choose between reference and device under test so that we can switch automatically and correct the data for that additional or different insertion loss on the path. So I hope with this demonstration we've been able to show you some of the most useful features that we've added to our systems for polarization-dependent, wavelength-dependent measurement to support measurements on photonic integrated circuits, silicon technology, and supporting wafer level and chip level testing. Thank you for your attention.